Hello all. In the previous video, we already discussed about cycle detection in an undirected graph using depth first search. So there are other methods also to find a cycle in an undirected graph. We can do it using BFS as well. But in this video, we will concentrate on union find algorithm. So using union find algorithm, you can detect the cycle in an undirected graph. Okay. Now, just look at the terms that are used in the algorithm name union find. So it's like union and the find. So the two main operations that are involved in this algorithm are find operation and a union operation. Okay. So you would have heard in mathematics, right? Sets concepts like 1, 2, 3 are the students, and 1, 2 belongs to some set, and 2, 3 belongs to another set kind. In usually in mathematics, you would have heard like this: 1 and 2 belongs to one set, and 3 belongs to another set. Like if you do union of these two, then what you will get? You will get 1, 2, 3. So whenever you do union, all will get merged. And you can say two sets are disjoint if and only if there is nothing in common between these two sets. Now if you look at these two sets, there is no element that is common. Okay, so we can say these as it disjoint sets as well. Okay, now this disjoint sets concept is mostly used in this union find algorithm. Let's talk about it. So, okay, now like first let's discuss in terms of sets concept, and then we will move to graph concept. Okay, now let us say you have a 1, 2, 3, 4, 5, 6, like till 10. Let's say there are 10 elements. Okay, let's consider this till 10 elements. Now all belongs to different set. Okay, like all these 10 elements are in 10 different sets. Now when I say when I say union of these two, like let's say like you do union of 1 and 2. Now first, before doing union, what I have to do is one and two are present in the same set. Initially all these elements are present in different sets, so there are 10 sets that are present, and each set has single element. Now like I'm starting union find operation for normal mathematics sets. Okay, 1 and 2 are in different sets. Okay, first I have to find out in which set 1 is present and in which set 2 is present. Okay, this is present in first set and this is present in second set. So since they are present in different sets, I can do union. So when I do union, now my sets will become, I'll have a set 1 comma 2 and single sets of these elements. Okay, now let's say I want to do union of 4 and 5. Okay, now in 4 and 5 both are present in, like first I have to do find operation. First you have to check whether those elements belongs to same set or not. If they belong to same set, then you need not do union operation because they're already present in the same set. Why you do union? If they are present in different set, then only you will do union operation. Okay, now here if you see 4 and 5, those are present in different sets. Since those two are present in different sets, I will do union of 4 and 5. Okay, now you will have 1 and 2 as one set, 4 and 5 as another set, and 3, 6, 7, 8, 9, 10 in different sets. Let's say I want to do union of 2 and 4. 2 comma 4. Now after doing this 2 union, let some other person comes and asks to do union of 2 and 4. First thing what I have to do is, first I have to find in which set does 2 belongs to. So 2 belongs to this set, and I have to check in which set 4 is present. So 4 is present here. Now when I do union, like since those are present in different sets, I can perform union operation. Now I'll perform union operation between these two elements. So when I say union operation between two elements, it's like you are performing union operations on two different sets. If I say that I'm doing union on 2 4, it means that I'm doing union of the set in which 2 is present and the set in which 4 is present. Basically it's the union of two sets. Okay, now you'll get a set which will have 4 elements, 1 2 4 5, and anyway you will have other elements 3 6 7 8 9 10. Okay, now done. Now other person comes and he says that I want to do union of 1 comma 5. Now see in which one element is present. It is present in this set. Now see in which set does fifth element belongs to. So fifth element also belongs to the same set. If both elements are present in the same set, there is no need to perform union operation. You will perform union operation only if they are present in different sets. Then only it makes sense to perform union operation. If they are already present in the same set, then you need not perform. So when I do this 1 comma 5, like when I find in which sets this belongs to, I'll get an answer that both belongs to the same set. Then I'll not perform union operation. So you have got some idea regarding the find and union operation of the sets, right? Let's move on to the graph. Like we'll apply the same concept in graphs as well. Okay. Now what you will do is initially you will like you don't consider these edges. Okay. Like just remove this graph from your mind, and you just got like you have 7 vertices in your graph. Okay, initially all vertices belongs to a different sets. So let's start from the beginning. Don't take this picture. So what I'll do is initially all these elements, all these vertices belongs to different sets. Like I'm starting from the scratch. So 1, 2, 3, 4 all belongs to different sets. Like it makes more sense if I write like this. Okay, 1 belongs to different set, 2 belongs to different set, and then 3 belongs to different set. How many vertices are there in the graph we have seen? 8 vertices. 0 1 2 3 6 7 8. Okay, and you have 0 also. Okay, 0 1 2 3 4 5. We'll write 8 vertices here. Okay, yeah. Now what we will do is initially you will assume that all vertices present in the graph belongs to different sets. Those doesn't belong to a single set. Now you will start from the edges. Let's take 0 1 edge. Let's take, I am considering this edge. Okay, now when I consider this edge, yeah, I'll consider this edge. So now you don't you're not thinking in terms of a graph. You just have 8 vertices, 8 or 9 vertices. Now let's start from the edges. There is an edge 0 comma 1. Now see which set 1 belongs to and in which set 0 belongs to. So 1 belongs to this set and 0 belongs to this set. So when you do find operation, you get that both belongs to different sets. So what you have to do is you have to remove these, and since you are doing union operation, because both belongs to different sets, right, then you will get 0 comma 1. So when I say 0 comma 1, I'll draw a graph here. Okay, I'll draw a new graph from whatever we are processing. We'll make a new graph from out of it. So you have considered 0 comma 1, and when you do find operation, you get like you came to know that both belongs to the different sets and you can perform union operation. Okay, there is a 0 comma 1, like you have this at 0 comma 1. Okay, got it. Now what is the next edge? Let us consider 0 comma 2 is another edge. Now in this sets 0, first what we have to do is first operation is the find operation. If you get the answer that both belongs to different sets, then you have to perform union operation. If both belongs to the same set, then it doesn't make sense to perform union operation, right? So now the second edge is 0 comma 2. 0 belongs to this set and 2 belongs to this set. So both belongs to a different set. So what I'll do is I'll remove 2 from here. I'll add 2 to this set. Okay. Now this I'll add this edge also to my final output 0 comma 2. Okay. Now what is the second another edge that will process? Let us assume I'll process 2 comma 4. Okay. Now see to which set 2 belongs to. 2 belongs to this set. Okay. 4 belongs to this set. Okay. Both belongs to different sets. When both elements belongs to different sets, then you can perform union operation. Okay. Now I'll remove both. Like I am just adding 0, 1, 2, 4 are belongs to same set. Now since you are processing an edge 2 comma 4, I'll add here 2 comma 4 as well. Okay. Now this is also done. Let's process 3, 4. Okay. There is an edge from 3, 4. Like first you do find operation. 3 belongs to this set. 4 belongs to this set. So since both elements belongs to different sets, then you can perform union operation. So this edge can be considered. When this edge can be considered. Okay. Now what I'll do is I'll remove this 3 and I'll put it here 3 comma 4. There is an edge 3 comma 4. What I'll do here is I'll just add 3 comma 4. Now let us consider I want to add this 1 comma 3 edge as well. Okay. Now see in which set 1 belongs to. 1 belongs to this set, and see in which set 3 belongs to. Okay. 3 also belongs to the same set. Okay. So when you get an answer that both elements belongs to the same set, you cannot find union operation. Whenever you encounter a case that both elements or both vertices belongs to the same set, then that edge will result in cycle. Okay. Now 1 comma 3, 1 2, there is an edge from 1 to 3, or you can say it as a 3 to 1 as well. When this edge, like I wanted to consider this edge to my final output, but while doing so, I got I came to know that 1 and 3 belongs to the same set. Now if I try to add this edge, then this will result in cycle. So from find and union operation, what you understood, whenever you initially all vertices belongs to different sets and you take edges one by one. Whenever you start taking edges, you do find a union operation. So while doing find operation, when you find that both vertices belongs to the same set, then that edge you should not consider, because that will lead to the cycle. If both vertices belongs to different sets, then you can form an edge using those two vertices. That is the simple concept. You take the vertices, just keep on doing this find and union operation. Whenever there are both vertices are in the same set, then say that there is existence cycle. If you don't encounter any case like that where both vertices belong to the same set, then you can say that there is no cycle. Okay, now I can say that there is a cycle in this graph. Okay, yeah, like let's say this is not there. Now I assume that this particular vertex is not there. Okay, this vertex edge is not there. Okay, I'll remove this. Now I'll consider this 4 comma 5 edge. So 4 belongs to this set, 5 belongs to this set. So both belongs to different sets. When both vertices belongs to different sets, then we can consider that edge. That edge will not result in cycle. So 4 comma 5. What I'll do is I'll write 4 comma 5 here. And here as well, I'll remove this and I'll add 5 to this set. All this 0, 1, 2, 4, 4, 5, 3 belongs to the same set. Now I'll process 5 comma 6 edge. So 5 belongs to this set, 6 belongs to this set. So both belongs to different sets. So now I can say that this edge can be considered in my output. So 5 comma 6. Here I'll add 6 as well. This is the kind of universal set as well. Now next edge what I would be considering is 6 comma 7. So now 6 belongs to this set, 7 belongs to this set. So when you do find operation, both vertices belongs to different sets. So what you can say is you can do the union operation. Now I'll do the union operation. I'll consider this edge as well. So I'll just do this 6 comma 7. Now there is one more edge 7 comma 8. Okay, so 8 belongs to this set, 7 belongs to this set. So since both belongs to different sets, I can consider, like I can do union. So this is removed. So like I'll consider this as well, like I'll add this edge as well. Now I'm done processing all the edges of this graph. So while processing all the edges, I encountered only a case, only a single case like 1, 2, 3H, which will result in cycle. So I'll not include that. Then if I don't include that, there won't be any cycle. So yeah, using a simple union find operation, you can actually perform, like you can actually detect the cycle in an undirected graph. So this we have represented, right? Let's represent this in form of a tree as well, because graph is also a kind of tree, right? So let's do that. So what we will do is, instead of taking like this in form of sets, because since we are working on the graph, you cannot consider initially these sets kind of thing. So what we'll do is, we'll represent the same concept in form of a tree. Okay, now you have these things, right? Let's remove all these things. I'll make a parent, like I'll have an array, okay, where I'll have parent for each vertex. Initially, uh, see, like what I'm doing is, initially all vertices belongs to different sets, right? So 4 is parent to, it's like this is one tree, this is one another tree. Like what I'm saying is, you have 9 different trees, because initially all belongs to different sets, right? So I'm just removing this set concept and moving to the tree concept. So when there is only a single element in a tree, we can say that the parent is itself. So what I mean is, let's say there is a tree like this one. So the parent here, it is one itself is the parent. Now if you have two vertices like this in a tree, then you will say that one is parent to two. But who is parent to one? One itself is the parent, right? So that's what I was trying to say. Initially all belongs to different sets. Then each element itself is its parent. So what we will do is, initially assign 1 minus 1 to everything. Like you have 9 like almost 9 vertices, right? So you assign minus 1 to everything, because now every vertex, like each vertex belongs to a separate set, and vertex itself is a parent. Okay, 1, 2, 3, 4, 5, 6. I'll add 3 more, 7, 8, 9 for each and everything. So here I start from 0, 1, 2, 3, because whatever the set concept to, like we have to represent in terms of graph, right? So that's why I'm just taking an array. Okay, so you have the 0, 1, 2, 3, 4, 5, 6, 7, 8. I represented the same thing. Okay, now I'll start the same processing. So when I start the same processing, first I'll consider the 0, 1 edge. So 1 belongs to different set, like 1 is a different tree and 0 is a different tree. Okay, so how you say that both are different tree? Because go to this 0 value, minus 1. Whenever you see minus 1, then you can say that 0, that itself is a parent. Okay, when I go to 0, I found 1 minus 1, then okay, that 0 itself is a parent, then I have to consider that 0 itself is a parent. So here when you go to 1, it also has negative value minus 1. Okay, my 1 itself is the parent, then I have to consider that. Now parent of 0 is 0 and parent of 1 is 1. So parent of both vertices are different, which means they belong to different sets. So here find operation, here you have done on sets. Here what you are doing is, you just switched to the tree concept. You have to find parent. Here you check that whether both belongs to the same set or not, right? Here what you have to do is, you have to see what is the parent of 0 and what is the parent of 1. If the parent of 0 and parent of 1 are same, then you can say that both belongs to the same tree. If the parent of 0 and 1 are different, then you can say both belongs to the different trees. Now here parent of 0 is 0, parent of 1 is 1. Then what you have to consider is, both belongs to the different trees, and now you perform union operation. So performing union operation is in the trees is like, either 0.1 to 0 like this or 0.0 to 1 like this. So what I mean is either point 0 like this or 0 to 1 like this. Okay, so this says that either make parent of 0 as 1 as parent of 0 or 0 as parent of 1. Now I'll go with this approach. Okay, now here one parent is itself, so one value I should not change it because one itself is a parent. So when you check the 0, zero's parent is now 1. Okay, now what you will do is you will update this minus 1. Okay, 1, right? So if you say like zero's parent is 1, instead of minus 1 you update it with 1. And one more thing here is you added two now initially when 1 was there was only a single element. Now since you have added 0, what you can do is you will update minus 2. Okay, yeah, I'll explain this later. Now for now you just consider minus 1 only because I am not changing minus 1. Okay, so here 1 itself is the parent. Now the next stage is 0 comma 2. Now see, 0 belongs to, what is the zero's parent? Zero's parent is 1. Okay, uh, 1 zero's parent is 1, one's parent is minus 1, one's parent is minus 1, which means that one parent, whenever you say minus 1, that element itself is a parent. So one's parent is minus 1, which means that this itself is a parent. And 2, what is the value of 2? Minus 1. Okay, 2 itself is the parent. So parent of 2 is 2 and parent of 0 is 1. So both belongs to different trees. Now what you have to do is you have to point. So here what you have to do is initially, now I have taken array like tree like this, right? 1 to 0. Now you have another 1 2. Now since both belongs to the different trees, what I can do is either point 1 like this or point 2 like this. So what I'll do is, let's say I'll point I make 2 as the parent and point 1 like this. Okay, now 2 1 0. Here if you see, now zero's parent is 1. Okay, zero's parent is 1, still you have 1. One's parent is 2, but here one's parent is minus 1, so you have to remove this, and one's parent is 2 and 2's parent is itself, so you can still put minus 1. Okay, fine. Now 2 comma 4, whenever you say 2 comma 4, so 2, like initially what is the, where like 2 exists in this particular tree. Okay, now check the parent of 2. Parent of 2 is minus 1. So when you say minus 1, it itself is a parent. Okay, so parent of 2 is 2 and the next one is 4. Parent of 4, go to 4 and its value is minus 1. Okay, when you encounter minus 1 value, then you have to say that 4 itself is the parent. So parent of 2 is 2 and parent of 4 is 4, which means that both belongs to a different sets. Okay, now you have this tree with just 4, right? What I'll do is I will point 4 here. Like you can do this way also. Instead of pointing, instead of making 4 as the parent, you can make 2 as the parent also. So if you make 2 as a parent, then you will get like this. But what I want to do is I want to make 2 as the, like 4 as the parent. So my tree would look like this. Okay, because I am moving these two things. Now here when you do this way, zero's parent is 1. Okay, zero's parent is 1. One's parent is 2. Okay, one's parent is 2. What is 2's parent? 2's parent is 4. Here 2's parent is minus 1. You will remove this. Okay, now done. What is 4's parent? 4 itself is the parent. So 4 itself is the parent, minus 1. Okay, done. Now next thing is I'll consider 3 comma 4. Okay. Now when you go to 3, you will see minus 1, which means that this itself is a parent. Okay, for 3 is the parent. Now the second one is 4. Now 4, you go to 4. For what is the value of 4? Minus 1, which means that it itself is a parent, 4. So 3 comma 4, both parents are different. So you can say that both belongs to different trees. Now you do union of these two trees. Okay. So you have this one 4, 2, 1, 0. There is a tree like this. Now you get 3. What I can do is either I can point like this. Like when I make 4 as a parent, your tree looks like this. 4, 3, 2, 1, 0. When I make 3 as a parent, it looks like this. 3, 4, 2, 1 and then 0. Okay. So this way. What I'll do is I'll make 3 as a parent. Now when I do this, 0's parent is 1. Okay. 0's parent is 1. 1's parent is 2. Okay. 1's parent is 2. Now 2's parent is 4. 2's parent is 4. Okay. Now 4's parent is 3. Here 4's parent, if you see, 4's parent is -1. When you say -1, then it itself is a parent. But you have to move it to 3. What is the 3's parent? 3 itself is a parent. Okay. What is the 3 value? -1. Okay. Done. We are done. Now let's consider this like this particular edge 1 comma 3. What is the parent of 1? 1's parent is 2. Okay. You have to traverse as long as you encounter a -1 value, because you have to find the like root node, not just the just the immediate parent. Now 1's parent is 2. You did not encounter -1. Go to 2. Okay, I went to 2. 2's parent is 4. I did not encounter -1. Go to 4. When I went to 4, its parent is 3. From 3, go to 3. Okay, when you encounter this. So my parent of 1 is 3. Okay, so if you see here, that is the same. Like 1's parent is 2, 2's parent is 4, 4's parent is 3. So the tree in which this vertex exists, what is the root node of that? It is 3. Okay, done. Now 3. What is the value of 3? What is the parent value of 3? -1, which means that 3 itself is the parent. So 1's parent is 3 and 3's parent is 3, which means that both belongs to the same tree. Okay, here even if you see 1 and 3 lies in the same tree. When you encounter this condition, then you can say that there exists a cycle. Okay. Now in the coming video, now if you see this way, right, you have to traverse many steps. It can be while doing so, whenever you are doing an union operation, like in this particular example, you would have done this way also. If you would have done this way, whenever you want to find the parent of 0, you just have to do 1, 2, 3 steps. But here you have to do 4 steps here when you are finding the value of 0. Okay, so it depends on how you are doing union operation. Sometimes it can be left skewed tree as well, right? So there can be some optimizations we can perform here, in which this find operation, like the number of steps you are taking to find the parent, can be reduced. Okay, that we will discuss in the next video, like where collapsing find and union by rank. So that we will discuss in the next video. Now let's complete the other edges as well. Now 4 comma 5. What is the 4's parent? 4's parent is 3. Okay, what is the 3's parent? 3's parent, 3 itself is the parent. Okay, now 3 is 1's parent. Okay, 3 is 4's parent. Now let's go to 5. 5 value is -1, which means that this itself is a parent. So 4's parent is 3 and 5's parent is 5. So since both parents are different, what you can do is you can perform union operation. Okay, 4 comma 5. What I'll do here is, this is our graph, right? 4 comma like 5 belongs to a different set, right? What I'll do is I'll make this way. Okay, 3 comma 5. This is little clumsy. Okay, 3 comma 5, I can do this. Now let's go to 5 comma 6. When I go to 5 comma 6, now when I do this one, when I make 3 as a parent of 5, I have to update this value also. 5's parent is 3 and 6 parent is itself. 6 parent is -1, which means itself. So both belongs to different sets. What I'll do is I'll add 6 here itself. Like ideally what I can do is I can make 6 also as a parent, but like I'll just consider 6 as the parent, like I'll consider 3 as my parent. When I make 3 as a parent, my tree would be like this. Like I'll get one more something like this. Now let's process 6 comma 7 as well. So 6 belongs to, when I do this way, when I make 3 as a parent, 6 parent should be 3. Okay. Now 6 parent is 3. And what is the 7th parent? 6 parent is 3. 7th parent is 7 itself is a parent. So what I'll do is I'll add 7 here. Okay. 7. Now another thing is 7 comma 8. 7 belongs to 7. When I make 7 here, 7's parent is 3. Okay. Now this parent is 3. And 8's parent is minus 1, which means 8 itself is a parent. Okay. Now 3 comma 8 both belongs to the, like both parent values are different, right? Which means that both belongs to the different tree. What I'll do is I'll put 3 only as a parent. I'll make 8 as a child node. Okay. Now when I do this, 8, here 8's parent is 3. Okay. Now we have done this way. So while doing so, what we have encountered is there was a case while processing 1 comma 3, we found out that both belongs to the same tree. And how did you find out that both belongs to the same tree? You found out the parent of 1. When you found out the parent of 1 was actually 2. And when you go to the 2, parent of 2 was actually 4. When you went to 4, 4's parent was 3. When you went to 3, 3 itself is the parent. So 1's parent is 3, and for 3, 3 itself is a parent, 3. So 1's parent is 3 and 3's parent is also 3. Here 3 and 1 both belongs to the same tree. So this is the condition here. So we can, what you can do is you have to just create an array, and initially each and every vertex belongs to different sets, right? So belongs to different trees basically. Then since both all belongs to different trees, that element itself is a parent. That's why we have assigned -1. And what you have to do is you have to take the each edge and find out the parent of each vertex. When you encounter parent values are same, then you have to say that there exists, like by adding the edge you will get a cycle. Else you can change the parent. Now this array concept or the parent concept we will discuss with one more example in the coming video. And as I was saying, while doing the union operation, right, there can be a chance, like there we get two options. Either make set 1 as a parent or set 2 as a parent. If you make set 1 as the parent, then your tree would be balanced, in which means that your height of the tree is reduced. But if you make 3 as a parent, then your tree would be left skewed. So when your tree becomes left skewed, right, while parenting, while doing the find operation, what you have to do is you have to go up, go up, go up, go up. You have to make multiple steps. So in this way, our time complexity for each find operation will become 0 of v. So how many times we are doing this one? We are doing for edges, right? For how many edges? 0, e edges. So whenever you do, like while doing the union operation, if it becomes left skewed, then the find operation takes order of v. So you have to do this find operation for each and every edge, right? So your final time complexity will become order of e into v. Okay. Because like it's easy to calculate time complexity here. Whenever you, for doing the find operation, you have to traverse like this, right? So in worst case, you might get a left skewed tree, which means that you will have like this, like all vertices pointing like this. So in this case, doing a find operation will take order of v, because all vertices are arranged like this. And since you are doing find operation for e edges, like how many edges you have, those many times you are performing the find operation. So your time complexity becomes order of e into v. So like as I was saying, you can, while doing the find, you can, there is a collapsing find and then union by rank also while doing the operation. If you do it in an optimized way, then you can, reduce this left skewed tree part. That we will discuss in the coming video. Thank you.